Welcome to the third and quite possibly last episode in this series called Driving Sustainability, the Role of Steel in the Automotive Industry. In this episode, which is entitled Green Steel and the Future of Sustainable Steelmaking, that's exactly what we're going to look at. Right, so Bryan, what we covered so far? So we've covered, let me think about this now then. Let me put the gain a bit down so far. Right, so last time we had a look at the producing steel for the automotive industry and producing steel in general, and we talked about how we could produce it via the blast furnace route, then the Boss vessel, and we looked at then how to use an electric arc furnace. We also looked at how both of those still produce or do produce CO2, so fossil fuels, no, not fossil fuels,
greenhouse
gas emissions, that's it. They use fossil fuels.
Yeah, that's right. Yes.
Okay. So that's, if we're going to then have a future of these green cars, electric vehicles,
Yep.
I suppose we need to start looking at how steelmaking process is, don't we? But there's one steelmaking process that we haven't actually covered, and this is the, what's it called?
Direct reduced iron.
Direct reduced iron, DRI, which gives us a bit of an advantage, doesn't it? Because it leads on to the subject of what we might term fossil-free steels. And fossil-free steels is trying to make steel without the use of fossil fuels.
Yes, or a reduced sort of use of fossil fuels, such as natural gas, for example.
And hydrogen as well, isn't it?
Hydrogen is in the sort of prototype stage, really. There's one pilot plant in Sweden with SSAB, who was the major steel producer in Sweden, and that's progressing well, as I understand it, but it hasn't been commercialised currently.
All right then. So in this episode, we'll call it, or this section, we're actually going to have a look at the DRI process, aren't we?
That's right. Yes.
Okay. So
Okay.
we need to keep in mind when we're doing this then that it's not a case of just producing steel. The automotive steel, the automotive grades of steel,
Yep.
which we've covered before, are quite specialised.
That's right, and the chemistry is more challenging for the automotive industry and for the packaging industry, for example. So that accounts for the fact that whereas for long products, the use of 100% scrap is widely used and is used then for the production of products such as reinforcing bar, commercial plates and bars, which have a sort of much more tolerant sort of composition, if you like, than for some of the more specialised applications for strip products, such as tin plate for packaging industries and also for automotive grades of product. So there are two commercial processes used for the manufacture of direct reduced iron. One is gas-based and the other is a coal-based process. The primary gas-based process is the Midrex process, which accounts for roughly 76% of DRI production in 2019. And the primary coal-based process is the Corex process, which accounted for 24% of DRI production, again in 2019. So if we look at the Midrex process to start with, it consists of a single shaft furnace where iron ore in lumps or pellet form are applied at the top of the furnace, and reducing gas is applied mid-furnace and ascends to the top of the furnace. Reducing gas is generated by burning natural gas in air in a methane gas reformer and consists of a mix of carbon monoxide and hydrogen, mostly carbon monoxide. So in this shaft furnace, the iron ore is progressively reduced as it descends the furnace from hematite, which is the most abundant commercial or iron ore product, which is a chemical composition of Fe2O3. And in this shaft furnace, as the lump ore and pellets progressively descends, it's reduced in stages from hematite, Fe2O3, to magnetite, Fe3O4, and then to worstite, which is FeO. So there's a progressive change in the ratio of iron to oxygen. So the ratio starts initially with 1.5 atoms of oxygen to 1 atom of iron, to one where it's 1 atom of iron to 1 atom of oxygen.
I guess this is hence the direct reduction.
That's the direct reduction process.
Right,
yes.
okay, yeah.
And it goes finally then out of the fast furnace, out of the shaft furnace. You end up then with metallic iron, although there is an additional sort of amount of material called gangue, which is composed of things such as silicon dioxide, aluminium oxide, calcium oxide, sulfur, and phosphorus. So that's about 3 to 5% of the sort of the product, which is called metallic iron, but is in fact more like hot metal, because it does contain this significant quantity of gangue material, which would make it inappropriate for application in any industry. So all these reactions occur in the solid state, and the waste flue gases which are generated, which you've mentioned, carbon dioxide is the primary waste flue gas. That's recycled back to the methane gas reformer, where hydrogen can be added to the natural gas to reduce carbon dioxide emissions.
Okay.
So I should also add that there's still a significant amount of carbon present in the product. You're talking about 0.8 to up to 3% of carbon dioxide. So as the consequence, you are sort of recycling carbon dioxide back to the methane gas reformer, then there's a reduction in the CO2 emissions from the Midrex process. So generally, you've got about 50% of the emissions now compared to a blast furnace Boss operation.
50%.
50%. So it's still quite a lot of carbon dioxide, but there has been a significant reduction. So if you compare the blast furnace to the Boss operation, then 90% of the carbon dioxide emissions arise from the blast furnace and material preparation operations, namely coke making and sinter plant operations.
And as we walked up the stairs earlier,
yes,
what did we see?
We saw the coke ovens in its final day before it closes altogether at Port Talbot. A sad day. Yeah. So typically 1.65 tons of carbon dioxide are generated in the blast furnace and material preparation stages in the sinter plant and the coke ovens to produce 1 ton of steel. So it's 1.8 tons of carbon dioxide to 1 ton of steel. So out of a total of 1.8 tons of carbon dioxide to 1 ton of steel, 90% of that occurs during that blast furnace and material preparation stages. So that's the Midrex process. So I mentioned that there's an alternative process called the Corex process, and that consists then in 2 stages. So there's a combination of a shaft furnace, as you've got with the Midrex process, and a melter gasifier.
I don't want to ruin your flow, Bryan, there, but something I'm a little bit confused at is you mentioned the blast furnace. The point is there that doing the making of steel via the blast furnace route. Yeah. You say 90% of the CO2 emissions come from the actual blast furnace and preparation. And preparation areas, the coke making and the sinter plant operations. So we can do away. You're saying that we can do away with that for the Midrex process. Yes. So the material preparations then are redundant. Right. Okay. At that point. So that's why you get such a big reduction then in your. That's one of the reasons anyway. Yeah. You get such a big reduction. Yeah. Okay, sorry to interrupt you. That's fine. Yeah. So in a similar manner as with the Midrex process, lump iron and iron ore pellets are applied at the top of the shaft furnace, and the carbon monoxide reducing gas is applied mid-furnace. So the same reduction process commences where hematite is reduced to magnetite and then to worstite, and the worstite then descends into the melter gasifier, which is located below the shaft furnace. So in the melter gasifier, heated oxygen is blown in at high velocity, as well as fine non-coking coal. So these react together to generate carbon monoxides,
which reacts with the wustite to produce, in this case, a liquid iron based product, which also contains typically 4.5% carbon. So again, far too much carbon to produce any sort of viable product, hence the need for the electric arc furnace then to convert that product into something which can be used.
Yes, and we'll come on to that after this, isn't it? Yeah.
So in terms of impurities then, as well as this sort of significant amount of carbon, roughly the same as the hot metal that's produced in the blast furnace. And from the blast furnace goes to the Boss plant, where there's a reduction then of a factor of 100 during Boss operations with respect to carbon. So you end up with a reduction from 4.5% carbon in the Boss plant to 0.04% to 0.05% carbon.
Yeah.
So it's an extremely efficient process for reducing the amount of carbon present. And the electric arc furnace isn't quite as efficient as that, which I'll go on to describe. Okay?
So we've now got this Midrex process and now Corex process, which is both producing a steel, which is almost like an equivalent steel that would traditionally then be put into a Boss vessel to reduce the carbon content.
Yes.
But obviously we're not going to do that.
No.
Because that's what we're trying to avoid.
That's right. So as well as producing that carbon monoxide in the melter gasifier, then carbon monoxide is also then transferred to the reduction shaft above. So this acts then as the reducing agent to cause that progressive reduction of hematite to magnetite and then wustite in the reduction shaft.
Yes.
So 45% of the total energy in the Corex process is used in the reduction process, and 55% is then exported for use elsewhere. So that's a sort of positive aspect, if you like, of the Corex process. And as with the Midrex process, the Corex process produces half the CO2 emissions of the blast furnace Boss steelmaking route. One of the advantages of the Midrex is it generally produces rather fewer carbon dioxide emissions than the Corex process. And that perhaps explains why sort of 76% of the DRI market currently for commercial DRI is produced via the Midrex process rather than the Corex process.
That was going to be my next question, so that's great. Yeah.
So there are three benefits then for going back to the Corex process, which I should have perhaps mentioned earlier. Yeah. There are three benefits to the process compared to blast furnace and basic oxygen steelmaking. There's no cohesive zone as with a blast furnace, which improves gas flow. Coal is used as and the reducing gas is used more efficiently. And finally, non-coking coal is used, so there's no need for a coke oven plant. So using basic coal without any sort of treatment of the material.
It's quite an advantage, isn't it?
That is quite an advantage.
But
I mean, when you've got a coke making operation, you do get rid of lots of impurities. So some of those impurities, therefore, will end up in the product that's applied to the electric arc furnace. So I sort of so that is a disadvantage, if you like, and I'll go on to discuss that in the sort of final part of this chat. And finally, there's an alternative method for generating DRI, and that's the production of DRI using hydrogen,
which is the big one, isn't it?
Which is the big one, and so you've got so the first example of such process is the hybrid pilot plant, which was commissioned by SSAB in Sweden in 2021, and a lot of other steel companies are interested. If this is successful and can be commissioned successfully to produce large volumes of steel, and that is the product of the future, because instead of generating carbon dioxide emissions, the emissions from that process are water and oxygen. So that's the preferred method going forward, but at this stage we're still reliant for DRI to make high quality steel products using either Midrex or Corex. So the process then is essentially, this hybrid process is essentially the same as the Midrex process with a single shaft furnace. So where carbon monoxide is substituted with hydrogen as the reducing agent, as I just mentioned. By this means the carbon dioxide emissions from the overall process are reduced by 90% compared to the blast furnace Boss steelmaking route. For this process to achieve this 90% reduction in carbon dioxide emissions, it is necessary for the hydrogen that to be generated via electrolysis of water to produce a combination of hydrogen and oxygen. This hydrogen is then classed as green hydrogen, providing it's developed using electricity, using renewable sources of energy only. So in SSAB case, there's hydropower available in Sweden. The alternative sources of renewable energy, such as solar panels and wind power, are obvious examples as an alternative to hydropower, if such a capability isn't available, which accounts for most steel production worldwide, really.
Yeah, I mean, that's right. So let's digress a little bit about that. So let's talk a little bit about that concept then of green hydrogen. So the green hydrogen is the holy grail, isn't it?
That's right.
It's an electrolysis process in which
Yeah.
we can make hydrogen using renewable energy,
Yeah.
and then it gets sort of downgraded along the way, and the colours change, don't they?
That's
so
right,
I
yes.
don't know for certain. I think isn't turquoise hydrogen something like it's been used with nuclear power?
That's right. Yes.
I think it might be
Yes,
turquoise.
right. I mean, the
Brown is with
Yeah.
fossil fuels, I think, is it?
There's grey hydrogen, which is produced using steam methane reforming, and that accounts for, I think it's virtually 99% of DRI production today. Of grey hydrogen today, which is not environmentally friendly at all. Then there's blue hydrogen, where it's a same process as steam methane reforming, but that's combined then with carbon capture and storage,
That's right,
which hasn't really been economically proven as yet. So that's still in the early stages of development. It's more expensive than the production of grey hydrogen. So there's a massive amount of research being carried out in the development of this carbon capture and storage process. And for example, the UK is investing large sums of money to try and establish a viable means of producing blue hydrogen with a combination of carbon capture and storage. So if we then go to green hydrogen, then it's far less than 1% of hydrogen production currently. So there's a lot of work being undertaken worldwide to establish an efficient, cost-effective method of producing green hydrogen.
Yeah.
And this is the major stumbling block, and is the key area where it's necessary to develop this product to ensure a viable, environmentally friendly process for the production of hydrogen.
Yeah, and I tell you what, it's a whole sort of conversation on its own, really, isn't it?
It is, yes.
So we'll go back to steelmaking for now.
So, yeah. So you're using electrolysis to break water up into a stream of hydrogen and a stream of oxygen.
Okay.
So if we move on then, so the DRI product produced from these various processes is then applied to the electric arc furnace. So, and that's then in combination with scrap of the appropriate chemical composition. So, for certain strip products, the chemical composition is more tolerant than for automotive and packaging applications, for example. So if you're making a radiator or a shelf out of steel, then there's a wider chemical composition tolerance than if you're making these very high quality products for automotive and for drawn wall iron applications, for example, in the packaging industry. So following electric arc furnace operations, then it's necessary to have secondary steel making to produce the exact sort of product that is sort of viable then for use in the packaging and the automotive market. And there's far more sort of emphasis on secondary steel making, because whilst the electric arc furnace does generate a product which is has significantly lower levels of carbon and other impurities, which are captured in the slag during electric arc furnace operations, it is not as efficient as the Boss plant in reducing carbon levels, for example, which are now typically around 0.5%. But if you're looking at automotive, there are products such as interstitial free steels. We're looking at levels of carbon and nitrogen of 0.003 or 0.004.
Incredibly low.
Incredibly low. So this imposes sort of increasing sort of stresses on the secondary steelmaking processes, such as vacuum degassing or vacuum tank degassing to generate ultra-low carbon level products. And there are certainly challenges as well in making some of the very high-strength steels that are required in automotive applications, such as dual-phase steels, ultra-high-strength steels, hot-forming steels, and trip steels. So there are certain issues where there's considerable further development work required in the use of electric arc furnace processes for satisfying all the requirements of the automotive market, say.
Well, okay, I'll try and sum this up so far then. So we've got DRI processes.
Yeah.
There's 3 types.
Yeah.
Well, there's 3 commercially...
Two commercially available.
2 commercially available. Okay, that's interesting. I'll talk about that. So the 2 that are commercially available now is the Corex and the Midrex.
That's right, yeah.
Okay. And then there's another one, which is the hybrid process, which hopefully uses pure hydrogen.
That's right, yes. And that's sort of I think it's gone beyond the pilot sort of stage at the moment, but it's still not sort of widely commercially available.
So all of those processes will produce a steel which is still not high quality enough for automotive. So it needs to go through another process.
Yes, because it's very much like the hot metal you generate from a blast furnace.
Yeah. So then that goes into the electric arc furnace.
Yes.
In which we add scrap.
Yes. So the amount of scrap that you would add then is dependent on the final application. So if you're making something with a challenging application, you'd use less scrap and more directly reduced iron.
Yeah.
Because you're obviously adding to the cost when you're using direct reduced iron. So 100% scrap is obviously the cheapest route. But there are major limitations in the use of many scrap products. So if you look at the scrap market, 75% of it is classed as merchant scrap. Looking at reinforcing bar and other applications where there's a very wide chemical composition tolerance. So that reinforcing bar is the largest sort of scrap pool, if you like, and the other 2 sources of scrap then are the sort of from within the steelworks itself. We're cutting off the end of a slab, or you produce a standard width through the hot mill, and you then need to reduce the width from, say, 2 meters to a 1.8 meter wide to satisfy a particular customer order. So there's that excess steel then, which is used, which is generated scrap, and all of these sort of products from the steel plant are of known composition. Whereas with a merchant scrap, then there's a whole variety of different sources, and the chemical composition is not sort of regulated or controlled to any great degree in the majority of cases.
Brilliant.
And the third source then, of course, is from end-of-life vehicles, for example. So typically a car company will have maybe 20 different grades of steel. So there'll be interstitial free steels, I mentioned, bake hardening steels, high-strength steels, ultra-high-strength steels, martensitic grades, dual-phase, complex phase, hot form steels, and so on. So, and within those grades, there are also sort of variations in the chemical composition. So if you take a typical dual-phase steel family of products, you've got a DP 600 grade of steel, which has got a UTS of 600 plus, a DP 800 grade, and a DP 1000 grade. Now the chemical composition of the DP 600 will be different to the DP 800 because to achieve the higher strength levels, there's a need to apply additional elements to the product. And the same then when you go from a DP800 to DP1000. So you need to be able to sort out each grade separately, but at least if you apply those to an electric arc furnace, then you have a knowledge of the precise chemical composition of those products.
Yes. Okay.
So scrap sorting can be very important then for certain grades of material from the electric arc furnace route.
Yeah, and it's a huge subject, scrap. We just touched the surface there. It's massive. So you can make long products, for, like you say, you've said before in the very beginning. From that, after that process, then, if we want a very loose sort of chemical composition to make long products, and we can do that at this point.
Yeah, there are some long products, such as special wire, for example, where there is much tighter control. But if you're looking at the mass market, then it's traditionally it's been 100% scrap, long products.
There we are.
But there's more money to be made in many strip product applications, such as the automotive industry. So consequently, you have the interest then from steel companies around the world to transform the electric arc furnace route, if you like, to a process which is also amenable to produce strip products, which will offer a higher profit margin.
And those premium products then that we're talking about, they have to go through another process. So they have to go through a process which is called secondary steelmaking.
That's right.
I know you've mentioned this already.
Yes.
And I've got written down here, there's 3 ways in which we can do that. They may not be limited to 3, but I've got 3 written down here.
Yeah.
One is the RH process.
Yes.
One's a vacuum tank degasser.
Yes.
And then we've got the CASOB process.
Yes. So if you take the RH process, then without going into too much detail, it's possible in the RH process to significantly reduce the chemical additions to iron which are present by using this process. So you start off with a ladle of steel, and from this ladle there's a progressive transfer of the material to a vacuum system which is attached to the ladle, and by doing this and by flowing steel continuously from the ladle, so that each ton of steel is actually progresses into this vacuum area over a period of time, then it's possible to reduce carbon levels, as I said, from typically from Boss plant operations of 0.04 to 0.05% to 0.003, 0.004% carbon and nitrogen, as well as getting rid of other elements as well. And during this process, then you can add the other alloying elements to the steel in this vacuum area. Now, and by doing this, then there's a much more efficient transfer of alloying elements to the product, so that there's no loss of alloying elements. Whereas if you applied these alloying elements during the Boss steelmaking route, for example, then you would lose a certain amount of these very expensive alloying elements in many cases into the slag.
Well, that's a very good point. It's not something we're going to cover here, but that loss of very, very important and expensive and sometimes rare elements during the steelmaking process is not something that can be ignored, but we are going to ignore it right now because we're not going to get into it. But it is an issue, isn't it?
Yeah. The vacuum tank degassing process is very similar to the RH process, and is used, for example, for the production of ultra low sulfur levels for pipeline applications. So there's a lot of similarity between the RH process and the vacuum tank process, whereas with the CASOB process, which is compositionally adjusted steel making with oxygen blowing.
Well done.
Then with that process, then it essentially is used for the large majority of steel products via the blast furnace Boss route. However, I don't have the answer to this, but if you use the CASOB process now for following the electric arc furnace route, because you've got higher levels of things such as carbon, sulfur, phosphorus potentially, than is the case with the blast furnace boss route, then would the CASOB process be appropriate for developing many of the strip products which you can develop using the blast furnace boss process?
Well, it's an invitation for someone to write in and tell us the answer to that question.
That's right, yes. I mean, the CASOB process, obviously, you won't go vacuum degassing. It's going to be a lot cheaper than the RH process, the vacuum tank degassing. So, but electric arc furnace isn't as reducing as the boss process. So I'm not quite sure how that problem's going to be resolved. And just sort of one final point on that, to improve the efficiency and productivity of electric arc furnace processes, it tends to be used increasingly as a melting process alone. So whereas in the past you'd have melting and refining over a period of hours, you're now talking about using the electric arc furnace as a melting operation only, and then refining taking place then later on in the secondary steelmaking process. So, for example, then in the electric arc furnace, you would typically melt all the steel, and then at the end of the process, you tip out 90% of the steel into a ladle, and you leave 10% of hot steel in the electric arc furnace. So when you apply the scrap and the DRI to the electric arc furnace, then it takes less time to melt the combination of scrap, DRI, and this material that's left in the furnace. So you're speeding up the operation.
Okay.
So that's called the hot heel practice.
Hot heel practice. Okay. How much or how many products, or what's the question here? Is the process, are the DRI processes that we're talking about, are they commercially operable for making automotive steel grades at the moment?
From what I've read in the literature, one of the leading sort of steel makers involved in this use of electric arc furnaces for strip products is Nucor in America. And there was a comment on the last paper that I read which said that there is a significant challenge in making certain grades of steel.
Okay.
I mean, the other factor to take on board, of course, is that there's a massive legacy of plant. So in many countries, they've invested in blast furnace boss steel making in the last 10 years or so. So to get a return on this investment, then the prediction is that by 2050, that because this legacy of plant, then the electric arc furnace route with DRI, say, will only probably account for, say, 15% of total steel production. So the large majority will still be down the blast furnace boss route.
Okay. Well, thank you for that, Bryan. I think we've established that making steel is not easy.
Yeah.
And it's a rather a hidden thing, isn't it? I mean, the electric vehicles and all that sort of thing are in our face these days, aren't they?
Yes.
They're there as you know, we need to buy them, need to use them, but the appreciation of the steel that goes into it is something that's probably not appreciated.
Yeah, that's right.
It's quite a complicated subject for anybody to understand.
Yep.
Just to give a plug, actually, when we were talking about elements that are lost in the steelmaking process, if you want to know more about that, then I've got a circular economy course, which goes into that in fairly good amount of detail. And is there anything else you want to say, Bryan, about some of the courses you do?
Well, I've got a course called Meeting Customer Expectations, which covers all the aspects associated with producing steel by the blast furnace boss steelmaking route, and the care that's taken in terms of producing the quality of product that satisfies the automotive market, and also looks at future grades of steel, following on from the LSAB project, the FSV, the Future Steel Vehicle project, which have been supported by most of the major steel companies worldwide. So in that course then I've got quite a lot of detail then to explain the limitations and the challenges associated with satisfying the automotive market in particular.
That's fantastic. And we've also got an electric vehicles course, haven't we? Specifically,
yes, and a tin plate course.
We've got tinplate course, yeah, but we've got a fossil-free steel making course.
That's right, as well, and many aspects that are sort of covered in on my electric arc furnace course are also discussed in some detail on that particular fossil-free steel making course.
And you're currently working on a carbon accounting course, aren't you?
Yeah, and I'm finishing off a hydrogen economy course.
There we are. So it all ties in together, doesn't it?
That's right. They're all sort of connected together with the objective of sort of achieving net zero carbon by 2050, really. So these are all contributory factors, if you like.
That's it. Well, we covered a lot there. We covered the traditional ways of making steel and the future ways of making steel.
Yeah.
Discussed the problems, discussed the exciting opportunities. Thank you very much, Bryan, for that.
Right.
And if you like this, let us know. And we may do more, because I quite like sitting down talking to you, Bryan.
It's nice to have a chat, isn't it?
It's nice to have a chat about something, isn't it? Other than the weather and things like that.
Yeah.
All right. Okay, cheers.